All right, our next Zoom marathon talk is Zachary Sylvan, HMS near SYZ singularities.
All right, thank you for the invitation. I hope it's been a impressive marathon so far. Yeah, so I'm going to talk about homological mirror symmetry near SYZ singularities. This is joint in progress with Mohammed Abu Zaid. And the wrapped part, which is the main thing I'm going to be talking about, is also with Alex Perry. So our local model near a singularity is this XMN. Let's make that blue. That's not blue at all, whatever. One more try. Oh, I can't undo. Okay. Well, there is no undoing. So this is product from I equals 0 to m of xi equals 1 plus the sum j goes from 1 to n of yj. And these are the singularities that show up in, or at least as the simplest singularities in the Gross-Siebert program. And our goal is just going to be to show that XMN is mirror to XNM. And we don't just want like some statement of homological mirror symmetry or SYZ mirror symmetry. We really want a kind of mirror symmetry that's compatible with gluing. So we want this in a way which is compatible with family Floer theory and that means really just gluing of SYZ fibrations. Now, concretely, this means that on the A side, we're going to want closed Lagrangians. We want a family of closed torus-like Lagrangian branes, closed torus-like branes, which is mirror to the space of points, closed points on the mirror. Okay. So before I talk about kind of how we're going to do that, let's just see what kind of spaces these are. So x0n, well, this is x0 equals 1 plus y1 plus up to yn. And this is just a copy of C star to the n, because all those y's live in C star. What is frequently going to happen is I'm just going to write down an equation and notice that, oh, I've already solved it for one of the variables. That's going to drop out. And that's what I'm going to use just repeatedly. Now, whoa, what is that? No? Okay, I don't know. Hopefully it doesn't stay on the next page. Good, okay. X and 0, well, that's x0 up through xn is just 1. There's no y's. And that also cuts out a copy of C star to the n. This time indexed by x1 through xn. So we can drop the x0. All right, C star is mirror to C star. Not super interesting. X11 is, in fact, a classic example. This is x0, x1 equals 1 plus y. Now remember, y is just in C star, so this is really x0, x1 is not equal to 1. This is C, C squared minus a conic, smooth conic, and that's well known to be self-mirror. I'm going to do one more example, which is x12. So x12 is x0, x1 equals 1 plus y1 plus y2. And what we can notice is that this has two C star cubed charts. By the way, can everyone read my handwriting? I realize it's pretty atrocious.
It's fine. It's neater than mine.
Okay. So two C star cubed charts given by x0 is non-zero and x1 is non-zero. Now, on the mirror, we're going to have x21. Let's put a comma there. So this is going to be x0, x1, x2 equals 1 plus y, I guess 1 plus y1. And so if I take this kind of the obvious projection to C, just 1 plus y, I'm going to have two special fibers. Well, there's going to be an empty fiber over 1, and there's going to be a critical singular fiber over 0. And this is the type of situation where we have our Clifford and Chekhanov torus. So we have our Chekhanov type torus over here, and we have our Clifford type torus over here. So that gives us two mirror charts. But one thing you can notice is that this is not all of x12, right? If x0 and x1 vanish, well, that's not in the image of these two charts. So over on the right, we must be missing something, right? And the thing that we're missing is this singular Lagrangian that passes through here. Now, the same story happens in x11, right? You have two charts here, x0 is not equal to 0, x1 is not equal to 0, and you have your Clifford and Chekhanov tori using the same projection. But in x11, this singular torus is immersed. It's just an immersed sphere. Whereas once you go to higher dimension, the singularity becomes worse. This thing is the Harvey-Lawson torus, and it's more badly singular, and we don't know how to do Floer theory there. So in general, we're going to have more charts. We're going to have m plus 1 of these C star to the m plus n charts. And they're given by just non-vanishing of all but one of the coordinates. And you get an obvious m plus n copies of C star. But just like in these easier cases, they're not going to cover all of XMN. So to get around this, we have two options. Either we can learn how to do Floer theory for non-immersed Lagrangians, or we're going to have to find a replacement for these things. And if it's not obvious, we're going to go for the second approach. So our strategy has two steps. So step one is going to be to construct an immersed Lagrangian. This is going to be L mn in x mn. And we're going to want to equip that with a space of deformation cochains. Def geo. These are going to be the geometric deformation cochains. All right, that's step one. And step two is we have to check that this is actually the right thing. So we need to identify the space of non-zero objects of def geo with the points in the mirror. Xn. That's the mirror. And in particular, we need to determine kind of which point a given object is mirror to. Which point a given object is mirror to. So that means that we need something that can distinguish points, which really means we need a mirror to the structure sheaf. Any questions at this point? Okay. So I'm going to talk about this part two. I'm going to talk about first producing a mirror to the structure sheaf. So that's where we're going to need to talk about wrapped homological mirror symmetry, because these are non-compact symplectic manifolds. The structure sheaf is supposed to see everything, which means we need a Lagrangian which sees everything. And if we're in a non-compact symplectic manifold, that Lagrangian had better also not be compact. And when you're doing non-compact Floer theory, you're doing wrapped Floer theory most of the time. Okay, so again, we have this standard projection, 1 plus sum of yj. And of course, this is the same thing as product of xi. And we map to C. And just like before, we have these two special fibers. We have a special fiber at 0, a special fiber at 1. So let's look more carefully at the geometry. So the general fiber is, well, the product of the x's is some non-zero value. So that's a C star to the m. These are from the x's. And then we have the sum of the y's is some non-zero value. So this is cross h, am I using a superscript? Yeah, hn minus 1. This is y. So this hn minus 1, this is the pair of pants. Sum of yj equals epsilon. Okay. So our special fiber, we have a singular fiber. At 0, modeled on, oops, not a sum, product of the xi equals 0. And we have a special fiber at 1. And so this is modeled on sum of yj equals 0. Now this is a sum of yj equals 0. That's a smooth hypersurface. We're not working projectively, but it's not the same as the other fibers, right? Kind of the generic fiber is a pair of pants, whereas this thing is a lower dimensional pair of pants cross C star. I mean, there's a C star action on it. The others don't have that. All right, so our Lagrangian which I'm going to call OMN, which is intended to be mirrored to O, is just going to be the positive reals to the M plus N, indexed by the, X1 up through XM and the Y, Y1, YN. So everything except X0, that lets me trivialize this C star factor. Yes, X0 is a choice. And if we had chosen a different X0, we would end up kind of getting slightly different Lagrangians, but the story would be essentially the same. So where does that live? That lives over here. Oh, that's supposed to be a 1. Whoops. This is a 1. This is a 0. You can see that it lives over that because all of the y's have to be positive real. So if you add 1 to some positive stuff, you get something positive. And the x's are just what they can be. Any questions at this point? Okay. So our theorem is that there's an equivalence of, and I guess I should say A infinity, whoa, how did it, that was weird. A infinity categories. So I want the split closure of the wrapped Fukaya category, X, M, N. And I want the DG category of coherent sheaves. I'm just going to write co, but this should be understood to be the DG version of X and M. And this sends OMN to O. So things to note, we don't actually need to exhibit this thing kind of fully explicitly. It's enough to show that OMN split generates. And has the right endomorphism algebra. Oops. Algebra. Right, because then you can just construct a map of rings and extend that to a functor on perfect module categories. Everything here is smooth, so perfect modules computes co. Now in our case, we're going to exhibit an equivalence that sends O to OMN to a line bundle. to some line bundle. And I want to mention this because it's not actually important, but if I don't mention it, it might seem like some important subtlety. Basically, I'm going to use descent formulas in the A side and the B side to match these categories up. And the conventions for the descent formulas end up producing a twist relative to one another. Obviously, people might have chosen different conventions had things gone slightly different historically, and then maybe they would just match up on the nose. So this is really just a matter of differing conventions. For descent formulas. On the A and B sides. Okay. So that's the theorem. How are we going to prove that? So the basic idea is that we're going to interpret XMN as a gluing. Oops. And I'm going to want to move this to the middle. Interpret XMN as a gluing. And we're going to want to put that over here. So how are we going to view this as a gluing? Well, we can cut this in half and separate those two special fibers and try to understand each side individually. And it turns out that basically every piece of this gluing has been studied before. So I'll start with the middle. So in the middle, we have the general fiber. So the general fiber, again, is C star to the M cross a pair of pants, H n minus 1. I'm going to actually move this to a subscript. I apologize, but I'm going to need some mirror pairs of pants soon. So I have the wrapped category of that creature. Now this is mirror to co on C star to the M cross the mirror pair to the pair of pants, H n minus 1. I'm just going to put mirror. And what this thing is here, this is the product of the xj. I'm going to say mirror xj. J goes from 1 to n equals 0. So in other words, this is the union of the coordinate hyperplanes in Cn. Okay, and mirror symmetry here for, well, I'm going to ignore the C star factors. This was proven by Lakili and Polishchuk. All right, let's work on this left-hand side. So on the left-hand side, again, we have this pair of pants factor floating around, but the interesting thing is that is what's happening with the x's, right? The x's are the coordinates that see something special happening at 0. So we have C plus 1 cross this pair of pants in the fiber, together with a superpotential product of the x's. So we're going to take the wrapped category stopped by that superpotential. I guess I could really say the Fukaya-Seidel category. This is, but I'm going to continue just writing wrapped everywhere. And over here, we have a cup functor that takes a Lagrangian in the fiber and parallel transports it over an arc on that side, kind of that goes along the stop. Oh no, I lost my notes. Okay. So this is mirror to, well, Cm+1 with that potential, that's just mirrored to a lower dimensional pair of pants. So this is mirrored to H, whoops, H -1. And then the pair of pants factor is mirrored to a mirror pair of pants. H n -1 check. And so again, we can take co here. Here we have some, this lower dimensional pair of pants is naturally a hypersurface of C star to the M. And so this is just some pullback along an inclusion, I upper star. And so mirror symmetry here was done by Abu Zaid and Aru. What's left is the right-hand side. So on the right-hand side, again, we're going to have a cup functor that goes to here, that kind of parallel transports over that arc. So we have another cup. And where does this land? Well, on the right-hand side, we have, so this C star to the M factor just floats around. We have the wrapped category of, we're going to have C star to the M cross. So now what survives doing something interesting is the Y's, right? So we have C star to the N together with a potential that depends on the Y's, sum of Yj. I could write 1 plus sum of Yj. I'm not going to worry about it. Kind of shifting around where the kind of superpotential is centered doesn't really change anything. Symplectically, the stop is viewed as living all the way at infinity. So I'm just going to write sum of Yj. So this is also a Fukaya-Seidel category. Okay, what is that mirrored to? Well, C star to the M just is still mirrored to C star to the M. And then Cn with this potential is mirrored to C star to the N with this potential is just mirrored to Cn. And there are various kind of people that have proved something like this. This is kind of one of the simplest examples of, I guess this is the simplest example of kind of mirror symmetry where one of the terms has a potential. This is a inclusion along a divisor, right? The mirror to the pair of pants is the union of the coordinate hypersurfaces in this Cn. So this is I left out a co, whoops. No. I lower star. And this choice of exactly which push forward functors and pullback functors we use doesn't really matter. I mean, here, I guess most things are Calabi-Yau, so it really doesn't matter. But even if it did, if I'm just concerned with piecing together the category, then I don't care if I've parameterized something with an unnecessary twist. I'm literally just trying to piece together the category. It's only if I'm kind of gluing two things to the same category that I really have to worry about the relative twist. Anyway, the instance of the mirror symmetry that we're using here, the one that ends up being simplest for us is to combine FLTZ and GPS. This is Fang, Liu, Truman, and Zaslow, plus Ganatra, pardon, whoops. and Shende. That kind of, we view this as a toric, an instance of toric mirror symmetry. And this kind of just gives the most direct way of showing that the wrapped presentation of this thing that we want to use does the right thing. Okay. Any questions about the ingredients before I kind of explain how we're going to perform the gluing? Okay. So the first thing we're going to do, well, after we've cut these things apart, right? We have something with 0 and we have something with 1, and we've cut these apart along this dashed line, and we're going to glue them back together. So, but I'm not going to glue them back together in one step. Kind of my favorite version of descent in the symplectic setting is where we glue back together, but we leave in a stop. I'm going to put this extra stop over here. So we're going to form the directed gluing. So this is X, M, N stopped by something I'm just going to call Y. So this is Y. And this just means glue, but maintain one stop. I could have put this stop at the top instead. You can, I mean, there's this global projection, so I could just move the stop around and those would be isotopic, but I'm just going to put it at the bottom. And what that means is that, well, we don't get any Rabe trajectories. Remember, or if you don't remember, the wrapped Floer theory is about counting Rabe trajectories. So kind of Hamiltonian flow near infinity. So this stop is going to get in the way of the flow on the lower edge, but on the upper edge, there's no stop. And so we do get trajectories. And what this is going to give us that we're going to get a semi-orthogonal decomposition. We're going to get W of X, N stopped by Y. I'm going to give myself a little bit more space. So the first part of the semi-orthogonal decomposition is going to be, let's do it this way. This is going to be the first part, right? Because then we're going to map to the second part. So this is going to be part 1, and this is going to be part 2. So the first part is going to be, well, the thing that was mirror on to the right-hand side. And I can look at my cheat sheet on the lower left. That's W of C star to the M cross C star to the N stop, or with potential sum of Yj. All right, that's the first half. And the second half is this thing mirrored to the left-hand side. So that's W of C M plus 1 cross, cross pants, H N minus 1 stopped, or with potential product of the Xi. Okay, that's my semi-orthogonal decomposition that symplectic geometry tells me I should use. If I had put the stop on the other side, I would have gotten the other one, and they would differ by some autoequivalence. All right, now I can apply mirror symmetry. So this is mirror to co of C star to the M cross Cn. And then I have co of some pair of pants h m minus 1 cross h n minus 1 check, this mirror, this union of the coordinate hyperplanes. And now we can stare at this and say, this thing, this right-hand side, is sheaves on something of codimension 2. And Orlov tells us that that's a blowup. So this is co of some blowup along h m minus 1 cross h n minus 1 check of c star to the m cross cn. Great. So the first step of gluing tells us that this directed thing is mirrored to a blowup. Okay, but we want the undirected thing. We want the one without a stop. So now we need to remove the stop. Remove the stop. The extra stop. And we have a formula for that too. So stop removal says that W of xmn is a quotient. We take W of the directed thing, xmn stopped by y, and we quotient by the image of this cup functor. And so this cup functor unfortunately looks like a cap because the stop's at the bottom, but that's the image. We take a Lagrangian in the fiber and transport it over that gray arc. So this is modulo cup, the image of cup of the fiber. So the fiber is c star to the m cross h n minus 1. Okay, and now again, I can apply mirror symmetry. So this is co of this blowup along h m minus 1 cross h n minus 1 check of c star to the m cross cn. And quotienting by, well, I'll just do it in 2 steps, modulo some push forward of co of c star to the m cross h n minus 1 check. And again, we know by descent in algebraic geometry that quotienting by kind of sheaves on some hypersurface is the same thing as just removing the hypersurface. So this is co on this blowup, h m minus 1 cross h n minus 1 check of this thing, c star the m cross cn minus, let me make a bit more space, minus c star to the m cross h n minus 1 check. Now, what copy is that? There's exactly one obvious copy, and that's the strict transform. So let me just make that clear. And there is something to check that kind of one functor is mirrored to the other functor, that this copy of coherent sheaves, or this copy of the wrapped category that we're quotienting by is the same thing as the strict transform. These are things to check that we have checked. In any case, the claim is that this is X and M. So let's do that. So the blow up along H M minus 1 cross H n minus 1 check of C star to the M cross C n. So this codimension 2 creature is a complete intersection, right? This first thing is given by some of these, I'm just going to call them Y checks, these mirror Ys, these yi check. This is I equals 1 to M equals 0. And this thing is given by the product from J equals 1 to N of Xj check equals 0. So each of these things is cut out by one equation. The functions that cut them out are transverse. So this is a complete intersection. And in that situation, we just have a nice, easy formula for the blow up. This is given by, do I want to switch that? Yeah. U times, no, I'll do it in this order. Oh, whoops, sorry. This is not equal to 0, right? This is the sum of the y's equals, 1 plus them. 1 plus that equals 0. 1 plus sum of I check. This is I goes from 1 to M equals V times product from J equals 1 to N Xj check. And this lives in C star to the M cross Cn cross P1. So the C star to the M, this is where the Y checks live. The Cn is where the X checks live. And this P1 has U and V as its projective coordinates. All right, this is starting to look better. What is the strict transform? So the strict transform of this hypersurface, C star to the M cross, what were we supposed to be looking at? Hn minus 1 check, Hn minus 1 check. Well, that means the product of the x's is 0, which is like saying U equals 0. So this is a locus. U equals 0. And so the complement is, well, I can divide, if the complement of this is where U is not 0, so I can divide by U. So this is 1 plus the sum from I equals 1 to M, yi check equals V over U times the product of the xj checks. J equals 1 to N of xj check. And so this is an C star to the M cross Cn plus 1. And so my coordinates here are the x checks and V over U. And so this thing is x0, oops, x0. And so this is the product from J equals 0 to N, which is exactly the formula for XMN, or XNM. All right, so that's how homological mirror symmetry here works. So as a reminder, what that buys us is that we had, we have this, kind of Lagrangian, which is mirror to O, and we've now computed its Floer theory. We've computed that it is in fact mirror to some line bundle, and so therefore we can, once we cook up our closed Lagrangians, we can test them against this thing and figure out what point they're mirror to. Okay. So in the last couple minutes, I don't think I have time to say that much about the actual construction of the closed Lagrangians. So let me switch to this different version. Page. Sorry, this will take, I should have planned this better. Paper style plain, great. Okay. Going back to here. Oops. So in our closed Lagrangians, if we look again at this projection, there's an obvious kind of, there's an immersed Lagrangian that lives in this base that we can view as a neighborhood of, or as a cable of the singular one. In the base, this Lagrangian was introduced by Seidel, and the only question is, what should we put over it? Now, there are two possibilities, basically. Oh, no. Wait, can you see this?
Yes.
I see the page saying fiber Lagrangians obvious solution.
Do you see like red text?
Yes.
Okay, great. So I'm going to skip the obvious solution. Basically, there's an obvious guess for what the fiber Lagrangian should be, but the Floer theory is complicated. Our alternative is that we cook up additional coordinates. So we have this standard projection, which I'm calling rho n. Our strategy is to cook up additional coordinates rho I for I less than n, so that together with the coordinates xi, these give a full family. So we have n row coordinates and we have mx coordinates. These end up giving a complete set of coordinates away from some divisors. And what this lets us do is we can completely understand holomorphic disks in XMN and holomorphic curves in general, because we can split them into this full set of coordinates. And so to piece them back together, you need to impose some incidence conditions, but basically this reduces holomorphic curve theory in this big complicated manifold to holomorphic curve theory in 2 dimensions or in 1 dimension with some incidence conditions. Once we've done this, we can use our split Lagrangian. We can introduce a split Lagrangian. We can introduce some deformations on this and compute that the non-zero objects in this deformation space are precisely the mirror. All right. I think that's my time. Thank you.
Okay, well, thank you very much, Zachary. Any questions for the speaker? You should be able to go ahead and unmute your audio if you'd like to ask a question. Okay, so let me make sure I'm doing this right, that we have, in fact, unmuted the audio. Can someone let me know if they're having trouble asking a question? Oh, okay. If not, then let's thank Zachary. And we'll resume in approximately 10 minutes with the next talk.